you're okay with counts?
I'm fine, yes, I can hear you, so that's fine.
Okay then. In 3, 2, 1.
Good afternoon. It's a mixture of showers and sunshine, really, because we still have these northerly winds, quite cold winds, in fact. High pressure just occupying the middle of the Atlantic, stopping any mild air coming along for a while. So it's a cold day again, quite a strong wind, bringing some wintry... My career started when I left school with A-levels in maths, physics and geography. Didn't really know what I wanted to do, but felt it would involve science of some sort. And I was looking in one of the career booklets, and the Met Office, the meteorological office, came on the list. I thought, now that's something nobody else has mentioned, really interested me. Joined up, and I've been working in meteorology ever since. I got posted to the headquarters of the Met Office as a programmer on their mainframe supercomputers. I did that for 3 or 4 years. I then got posted to London Weather Centre. When I walked in the door, Jack Scott, who was in charge of the system then, he said to me, "You're the new weatherman. Follow me for a fortnight and you'll be on television." So that was how it started. One of the first things that has to happen to make a weather forecast is to observe the weather. We need to measure where everything is before we can analyse it and predict where it's going to go to next. For example, this chart here shows plotted weather reports from all around the British Isles, and one of my first jobs when I come in on a shift is to draw isobars, which joins the lines of equal pressure, and as many will know, the spacing of the isobar determines how quickly the wind is blowing. The charts that I draw in the office here don't actually get on the screen. I think they're works of art. I think they could stand their ground there, but no, the charts that you see on the screen are the results of the mathematical models calculations of how the atmosphere behaves. If you can imagine the world is split up into lines of latitude and longitude in our weather world. They're not latitude and longitude, but they're crossover lines. And the spacing of these grids of lines where they cross over determines the resolution of the model. At midday, for example, all of these values, these readings, are combined into what we call the initial field of the model. We'll see that the model has areas of cloud and rain, and it's taken those grid points and it's said there's rain at that point at that time, or there's cloud at that point at that time. Now that's the result of a very state-of-the-art model on your television sets. 40 years ago, we had no idea that we could get that sort of luxury of resolution. And there are models like this available on the internet at home. You could go home and you could go into your school IT lab and you could call up the results of these models and see how the equations are being solved to produce values of complex things like the weather.
Audrey Stewart, yeah.
Here I have the first frame of the sequence that we made in the weather office, and I have a little button, a clicker, that allows me to start the whole procedure going. It's like running your slides, your family photos from the holiday at home, and you set the world spinning, and then if I click it again it moves on to the next chart. And because I know how these charts have been prepared in advance, I know what order they're coming up in, and I will just talk to this. And to a weatherman, these are my script. I don't actually have the words written down on anything, but because I've been looking at the weather in the office all morning, this is my script, and I can say as many things or as few things as I need to occupy the time.
At the minute, Jim, we're under by 26.
I will get a message in my earpiece just before I go on air. At the end of the last news story, they will tell me exactly how long I've got, and it might be you're going to be 30 seconds under, it'll be a bit shorter, or you're going to have an extra 20 seconds. I've got to have in my mind's eye what 2 minutes and 30 seconds looks like, and if I'm given an extra 20 seconds, what impact that will have on the total package, and therefore how quickly I have to get through the sequence of slides. And the important point is, you almost have to average it out in your head as you go along, because what you don't want to do is suddenly have a shorter period of time and having just ambled your way through the early bit, and then find you've got to speed up right at the end, because that serves nobody. And what one has to do is to take an average pace through the whole thing. So you are constantly adjusting. It can be a daunting feeling if you let it, because if you stood here and thought, what would those millions of people look like if they were all arrayed out there in front of me? And it would be quite challenging. It's like your worst nightmares of having to read in assembly or something. I can remember those feelings. But on the other hand, because you're in a position where you're talking about a subject which you specialise in, and you're across the subtleties of what you've got to talk about, it's not intimidating in that sense. And actually, to be honest, in most modern television studios, you're pretty much here on your own. There may be a co-presenter here, there may be a floor manager, but a lot of the time you're looking at a camera on its own. and that isn't all that intimidating. But behind the scenes, there could be all sorts of problems, and the people who do have a difficult job are the people in the control room, and they have to be making split decisions that impact on which story stays in, which one gets dropped, in seconds. And that is a very tough call.
Presenting the weather on television is only a part-time job for Jim Bacon. The rest of the time, he is a director of a meteorology company called Weatherquest, based on the outskirts of Norwich.
Weatherquest was formed in 2001 as a small company of 3 or 4 people, and we decided to embed it here at the University of East Anglia because the university is well known for its climate research, and from that time we've grown it to now have 13 people employed, and we're involved in a whole range of activities. Weather is something that's really important for all sorts of organisations in the economy. So we do media work, we do work for insurers, we do work for farmers, and indeed for construction companies whose operations are also sensitive to the weather. So there's hardly anyone out there who isn't affected by weather conditions in one way or another.
I started in Weatherquest in 2003, shortly after I finished my degree. Weatherquest is based at the University of East Anglia, and that's where I did my degree. And shortly after finishing that, I moved upstairs and came to work in the office here. This morning I've got a lot of things going on. I'm working on the newspapers for tomorrow, making the maps, writing the forecast and collecting the data from yesterday's weather. And I'm also looking at some insurance calls as well, talking about past weather and seeing how that could affect some insurance claims. The best thing about working with the weather is that every day is different. No 2 days are going to be the same. It's always a real challenge to find out what's going on. You've got all your information to come together, tying it all up and getting a good forecast that you can hopefully put across to someone else and they'll understand and hopefully have a better idea about what to wear, for example. It can be quite hard. Obviously the weather works 24 hours a day, 365 days a year, so we work shifts here. Some early starts in the morning, waking up at 4 o'clock in the morning to do the early morning radio shows can be a little bit tiring, and working weekends, but other than that, it's a really very good job.
Maths is crucial for weather forecasting. We need to be modelling on a computer how the atmosphere is behaving all around the world. And so at millions of different points in the atmosphere, we need to be doing mathematical calculations of how things like temperature and moisture in the atmosphere and wind are going to behave, not only in the next hour, but in the next days and in some cases over the next weeks. There's a lot of calculus that comes into that activity, and it's done using forms of equations known as finite difference equations. So there are quite literally billions of calculations that have to be made every time a computer model runs to make a weather forecast. Things can go wrong in a weather forecast, as everybody knows. It's not usually to do with the mathematics actually of the problem. That's more commonly to do with limitations to our physical understanding of how some processes in the atmosphere work, and also the fact that we can't always model the atmosphere at the degree of detail that's needed. So while we may be able to model how a big low pressure system is behaving, we still find it very difficult to model how an individual cloud might be behaving, and that's because we can't always do enough calculations in the time that we've got available to go through that process. The other point, of course, is the fact that we're not measuring the weather everywhere, so we don't have a perfect picture of what the starting conditions look like. So we have a simplified starting picture which will inevitably, due to chaos theory, lead to an inaccuracy as we move forward in time. As it stands, we're quite good at doing weather forecasting for the next 5 days. But once we get out into 7 days and into the second week, there's a lot for us still to improve on. I think there's a broad recognition that individuals have a lot of experience to bring to the problem, and it's not just the power of the computer that's important, it's the way we describe how the weather works in those computer programs, and there are things that we still don't know about those physical and mathematical processes which make it such an interesting area to continue working in.
Nowadays, climate change is of course uppermost on the mind of meteorologists. They have a major role to play in understanding and communicating the problem.
The weather has great variability here in the UK, and it's perfectly possible to have mild snaps in winter and then cold snaps. And of course the media is very quick to jump on those and to ask difficult questions about whether this is evidence of global warming or whether in fact it's contradictory to global warming. And the point that we would make is that the weather varies naturally as well as being forced by our human behaviour. And from on a day-to-day basis, we're seeing a lot of evidence of the natural variability, but we're also seeing an increasing number of occasions where a month goes by and it's yet another month that's been warmer than average or wetter than average. And so when we talk about those statistics on the television or on the radio, often it is an opportunity to say, and this is consistent with climate theory.
The next question is to say, well, who's to blame? And one of the things that they can do with this is that they can look at the mathematical models that we use to predict the weather in the short term and refine them in a way that allows them to run for, say, not just 4 or 5 days ahead, but to run them for decades ahead and to come up with averages in the future world, not the averages that we've measured in the past, but averages in the future. And those climatological model averages can show up a lot of interesting things. So we can do the experiments that in reality we wouldn't be allowed to do. So we can play at being God with the whole climate system. And we can run those models again and we can see what the effect is. And at the end of the day, the only way you can model the change in the climate that's being measured currently is by making an explicit addition of mankind's contribution due to burning fossil fuels. And that sort of acts as a pretty good, it's you.
I think that because weather forecasters are in such close contact with the general public on a day-to-day basis, whether it's through the television or on the telephone or whatever, we have a responsibility to try to make sure that the messages that we're giving out are A, consistent, and B, take the opportunity to explain the physics and the mathematics behind what's happening.
I think the thing that makes weather forecasting so appealing to me is that I look on it as a physics experiment. And when you're at school, you'll go into the physics lab for a practical, and a new experiment will be set up, and you'll deal with it and learn something from it. I have a new experiment in the subject that I love to deal with every single day. It's a new experiment been set up, and the physics that's operating in the atmosphere is different each day, and I have to determine what those rules are and apply the mathematics to that problem to solve which particular bit of physics we need to look at most closely. And it could be to do with heat exchange, forecasting at what rate the temperature will fall, how quickly, for example, the roads might go below freezing and make them icy. It could be to do with how fast the winds are blowing, forecasting for aviation, deciding how quickly the headwind is blowing against an airliner flying across the Atlantic. It could be how big the seas are going to be. If you're sailing on a ferry across the North Sea, you have to make calculations to work out how big the waves will be. All of those things involve the use of mathematics and the use of physics, and it's different every single day.
It's really hard sometimes to see how this maths makes sense, but I think definitely working in the weather, you suddenly start realising, tying things together, looking at the way you use statistics to try and understand how this month's weather's been different from average, and looking at the way different units work together and conversions between Fahrenheit and Celsius. It all does all tie together, and looking at all the even more complex math that you use in the mathematical models to actually model the weather. It does all tie together eventually, but you've really got to persevere with some of it, I have to say.
I was involved in forecasting for the power industry. Temperatures influence the demand of electricity. And I think it was said then that if we didn't have weather forecasting that allowed the generating industry to plan when to take power stations down for servicing and maintenance and when to keep them running, to cover that uncertainty without forecasting, they would need 25% more power stations than they had then. Power stations are big, expensive things. And that's just one example. So although meteorology can't come up and tap you on the shoulder and say, look, you owe us many billions of pounds for the services it provides the economy, you can look at meteorology and say, the bit you see on television is a tiny bit of it. All the rest of it is going into making better decisions. And it's all driven by an understanding of maths and physics.
Kim, thank you very much. From us, goodbye.